Welcome to the 27th lecture video for Physics 4C. In our class, of the optional topics we can cover, we are choosing to cover nuclear and particle physics, skipping solid-state physics. So, we are starting with the nuclear physics in this lecture set. We start with a historical introduction to the discovery of radioactivity and the three different types of radiation resulting from radioactivity. That is alpha, beta, and gamma rays. Alpha and beta rays in particular are involved with nuclear reactions, alpha and beta decays, reactions in which the type of isotope changes. We have a couple lectures in which we talk in some conceptual details about nuclear fission and fusion. And we will end this lecture with a take on a beta decay process, which we will revisit in the next lecture as we start particle physics. As you will see a hint of it in the last lecture segment, as we start to get into particle physics, special relativity dynamics is going to become relevant again, as particle physics is the one area of study that combines quantum mechanics and special relativity. So do read the textbook, but just so that you know, I'm kind of skipping around. In fact, think where I start will be a little bit before chapter 10, section 3. That's the historically correct place to start. So last time we actually talked a little bit about X-rays, right? Do people know how X-ray was first discovered?
From the cathode rays?
Yeah, cathode rays. What are cathode rays? Electron. Okay, let me rephrase it. So discovery of X-rays. So there's a device called a cathode ray tube. How many here have heard of something called a CRT? That's how people used to make TVs. And those old TVs, this stands for cathode ray tube television or screen or whatever. So what a cathode ray tube is, you have a cathode in a vacuum tube. Anyone here know the distinction between cathode and anode? Yeah, which one is positive? Cathode is positive? I thought cathode was negative. Cathode is the one that emits electrons, so it's got to be negative, right? Yeah.
Cation is. Yeah, sometimes it's confused.
Never mind. I know what a cathode is. I don't need to know what cation is. Okay, so cathode. So the cathode ray tube is, imagine an evacuated tube, and you have an electrode poking inside. And so this is physics, so this one I know. This electrode has to be negatively charged. So it's negatively charged by, you can do it with a battery by use of high voltage device or something. Let me label it as, so you hooked this up to some negative high voltage thing. So it's negatively charged. Then what people figured out is that there are some kind of particles that's emanating from this cathode. If you charge it negatively enough, then there are just particles that kind of come out of it. You can visualize these particles in many different ways. The way your old screen television does it is you have a glass here, and you coat it with some fluorescent material that when it's struck by one of these cathode rays, it'll glow green. That's the old monochromatic green screen that you may have seen. Or if you fill up this tube with a little bit of gas, like argon is common one, then you will see a green glow as these particles kind of move through the gas, exciting the gas. So you can kind of collimate the beam if you want, put some barriers here and here, and then this kind of geometrically limits where the beam can go. So with this collimation device, you would have a kind of cathode ray that goes like this. Okay? So this is this ray is what people would call cathode ray. And so cathode ray tube is that device. And I hesitated when Gauge said the cathode ray is electron. The subtle distinction is cathode ray is a beam of electrons. Right? When people were initially studying these devices, they didn't know what cathode ray was. But so the discovery of electron is credited to J.J. Thomson. He's the one who kind of identified it as a distinct particle, separate from any other elements, any other atom. It's its own particle. He characterized its mass to charge ratio. You guys actually, well, for those of, I don't know if you guys do it at Laney and other campuses, but here we have a E/m experiment in physics 4B, where you measure that charge to mass ratio of the electron, cathode ray. So what cathode ray is beam of electrons. So what you should imagine is this is really emitting these electrons, and you can make an arrangement so that maybe these two plates are charged. So you have a negative high voltage here hooked into positive high voltage here. So it's like a battery connected to both of them, except it's a super high voltage. It can be thousands of volts or tens of thousands of volts or even hundreds of thousands of volts. Then when an electron goes here, and if many of them will hit this target, but if it ends up going through, then the electron that's moving out here might have as much energy as, so if let's say that the voltage difference here, delta V, is about 100 kilovolts, 100,000 volts. Then after electron goes through this much potential difference, it'll have kinetic energy of about 100 kilo electron volts, right? Yeah. All this is actually, it's fairly doable. 100 kilovolt is not that high as far as high voltages go. People can put like megavolt on a, well, you can, 100 kilovolt, it's small enough, you can actually get that on that device. That Van de Graaff generator, if it's clean, free of any nicks and defects, then that can get 100,000 volts. So people were playing with this device, they were doing experiments with it, and this is what they discovered. Somebody, I'm gonna say Röntgen, one of the German physicists, he discovered that if you put a photographic plate here, some kind of film, photographic plate, something that'll be activated if light shines on it, that after a while, this would be exposed. I guess somehow he traced the source of the exposure back to cathode ray tube. And that probably happened through barriers, I'm assuming. So he started putting other things, like let's say a block of wood between the cathode ray tube and the photographic plate. And this photographic plate would still be exposed. So he attributed it to something that's coming from this plate. It's not the cathode ray because the cathode ray is stopped by this plate at the end. So there's something else that's coming from here. Something else that's coming from here. And whatever it is, it's something that's able to pass through wood. It's able to pass through a lot of materials that visible light can't really. And it's a strange property. People thought it was strange, so this was named X-ray as a kind of, well, it's a strange ray. It seems to go through a lot of material. We don't really understand what it is. This is before development of quantum mechanics. This is like 1870s or 1880s, 90s. So it was called X-ray. But I guess to an extent, from an experimentalist view, this is fairly easy to understand. The moment you turn off this cathode ray device, this X-ray also turns off. So it's something that's coming from cathode ray tube. When you have these high energy cathode rays that are suddenly stopped, then it emits this X-ray. Now for us, with the perspective of quantum mechanics, we understand what all this is, right? Kinda. What kind of particle is X-ray? It's a photon, right? It's a high energy photon. So what's going on is that this electron with the energy of 100 kilo electron volts, let's say when it suddenly comes to a stop here, then it's emitting this, its energy is being lost as light. So this light, what this is a photon with energy of 100 kilo electron volt. That's really what that X-ray is. This high energy cathode ray or high energy electron is losing energy as it's suddenly coming to a stop, and that energy is being carried away by a high energy photon. Okay? But it's an exciting thing for people to study. And now the rest of what we are talking about with the nuclear physics actually has nothing to do with the X-ray. The reason I started the introduction with this is because it leads to a discovery of something called radioactivity. So discovery of radioactivity is what I really want you to talk about. And the reason people noticed the radioactivity was because people who are working on similar things as this discovered something that was emitting radiation that was similar to X-ray. But unlike X-ray, it wasn't coming from cathode ray tube. It didn't have a power source. You couldn't turn it off. It was just coming from some material. So that discovery is described in your textbook here. And I will just tell you the story briefly, maybe. I'll tell you the story. I'm not sure if it'll be brief. So Becquerel is the guy who discovered radioactivity. And I guess this is the sort of cartoon illustration, so you can read that too. Either works fine. Cartoon illustration would be, so the X-ray was discovered with exposure of photographic plates. And radioactivity was discovered in a similar way. Somebody, for some reason, stored photographic plates near some material. This guy, Becquerel, was studying uranium salts he was studying some fluorescence or something. And he happened to store these photographic plates near uranium salts. And this is kind of one of the weird things. It's kind of easy to imagine how this discovery wouldn't have been made. So he had the photographic plates stored here near some material that he didn't know had a special property beyond the fluorescence. And for whatever reason, he decided to develop these unexposed plates. Who knows why he did that? But he decided to develop these plates. And when he did, he found out they were exposed. That's, I guess, when he tracked down, it was stored with uranium salts. So this uranium salt must be emitting some kind of ray that's X-ray-like. But it's obviously not an X-ray because we know how X-ray is produced. So whatever this is, it's a strange kind of radiation like X-ray, but it is not quite X-ray. But this is the beginning point of study of radioactivity. Because with the radioactivity, it's very specific to material property. So most of the things you see around you are not radioactive. I think we are legally required to stay that way. We are not. People used to work with radium, like painting clocks with radium, and you Google search radium girls. There's some big lawsuit about how people running the company didn't properly inform their workers of the hazardous conditions they are working under. So radioactivity, it's material specific. So uranium is one element that has a lot of radioactive isotopes that we'll talk about. And so once this was discovered, then a lot of other people were looking for more radioactive elements or elements that have radioactive isotopes. I'll just throw out some names so that you know some people who've done a lot of work in radioactivity. One is a guy named Rutherford. Does that name sound familiar? Yeah, he's the one who did the Rutherford experiment. He used the alpha rays there. Those alpha rays come from radioactivity. So that would be americium, but I don't think americium was discovered then. The other person, I mean, there are many other names, but at least the two that I should give you is, the other person is Mary, I'm not gonna be able to spell her name right, Mary Curie. So she's one of the few people who have 2 Nobel Prizes. I think one in physics, one in chemistry, I think. And she discovered a lot of radioactive elements. One in particular is easy to remember. She discovered the polonium. And the reason it's easy to remember is because she's a scientist working in France, I think. And she named the polonium after her home country, which was, I guess, I don't know, being ruled by Russians at the time. I don't know who would be ruling Poland back then. But so polonium is one of the radioactive, or one of the elements that have radioactive isotopes. And I guess we'll mention some of this. And when we get into these radioactive isotopes, one thing you will notice is that when you look at the periodic table of elements, a lot of these radioactive isotopes, they will be somewhere, they are all somewhere down here. They are at the high N value or high G value. So uranium is element right here, element number 92. Polonium is, where's polonium? Pu, right?
Oxygen, sulfur, 84.
Oh, 84, yeah, polonium. And americium is a common alpha source that's used in your smoke detectors. So a lot of these radioactive elements, they'll be found here. Cesium there are radioactive versions of cesium. So people started discovering, once they figured out this is something that happens, they started looking for other elements that have exhibit similar kind of behavior. And one of the main work that was done by Rutherford was he categorized the rays coming from the radioactive elements. It turns out these radioactive, or the rays from radioactivity, are more complex than X-ray. It has multiple components. So this is the place where the study of radioactivity enters. It's radioactivity, it emits ionizing radiation. And this strange feature that Becquerel noticed was only one component of radioactivity, but the other 2 components that wasn't part of this is also a type of ionizing radiation. And it's something to be careful with if you ever work with them. And your textbook chapter 10, section 4 lists all 3 types here. And this is a very handy graphic that kind of, in one picture, shows you the property of these 3 components that are emanating from radioactive elements. So let me just list them here. So the 3 types of ionizing radiation that come from radioactivity are alpha rays, beta rays, and gamma rays. And they all come from radioactivity. And in fact, as far as the definition is concerned, that's the real distinction between X-ray and gamma ray. I mean, there's a kind of typical energy range for X-rays and gamma rays. Typical energy range for X-rays, it goes from 1 keV to maybe 100 keV. And typical range for gamma ray, it usually ranges from around 1 mega electron volts and up. That's the typical energy range, but that's not what defines gamma ray. what defines gamma ray is that it's a high energy photon that comes from radioactivity. Oh wait, I kind of gave away the punchline. So when you, so these alpha, beta, and gamma rays, they were given these names for a reason. And this is the picture that kind of illustrates why they are categorized that way. It's, people here know Greek letters? Like you know A, B, C, right? When you learn Greek letters, these are the first three Greek letters, alpha, beta, gamma. And then delta? Yeah, I think, anyways, alpha, beta, gamma. So scientists, physicists, these are a little bit more creative when they are naming particles. Back then they weren't. So Rutherford was the guy who worked on these different classification of particles. And I guess he wasn't all that inventive, so he called them A, B, C, essentially, except in Greek. So the way he categorized them is by their penetrating power. You can see that in this picture here. Alpha ray is the least penetrating particle. So I guess I should give the typical energy ranges that people see. Alpha rays, so let me write down the kinetic energy. Kinetic energy of alpha rays range around MeV, 1 mega electron volt, or between 1 to 10. That's a typical energy range. And alpha rays are blocked by almost anything. In fact, air stops it. So if you have about this much air, as alpha rays go through the air, colliding with the air molecules, it would get stopped completely pretty quick. And in fact, now as it's stopping, it ionizes the air around it. And that's how the alpha rays in your smoke detector coming from americium is supposed to work. It ionizes the air around it, and that's affected by smoke particles. That's how your smoke detector works. So alpha rays, that's stopped by anything, it's stopped by paper, piece of paper. So this means alpha ray has a very distinct characteristic that's different from beta or gamma. In one sense, alpha rays are very safe, because if I have a very strong alpha source sitting here, I can kind of just stand far away and the alpha rays won't reach me. The air will stop it. In fact, do you guys remember, like in cartoons or whatever, when you see like radioactive rod, you see glowing in green hue, right? What that is it's all the alpha rays emanating from that. That's ionizing the air, making the air fluoresce. That's why they glow green. That radioactive green is coming from this. And it's it's easy to shield against. But the picture kind of flips around the moment the alpha ray source is on the wrong side. As long as it's outside my body, it's one of the safest thing to handle. We just don't, we just don't get too close to it, or if you have to handle it, you wear a glove. The moment it's inside my body, it's the most dangerous thing. Because when you look at beta or gamma rays, there's a good chance that gamma rays will just pass through my body without doing any damage. Alpha rays are guaranteed to react with something in my body and cause cancer somewhere, wherever it is. So one rule with the alpha ray sources, don't eat it, please. You think I'm joking. So that means
It happened kind of recently, right? The Russian spy or something?
polonium poisoning? Yeah. Yeah, that's how they died. So don't eat it, please. And if you are working with alpha ray source, what that amounts to is most of the time you will be working with a sealed source, as in you won't be touching it directly. But if you do touch it directly for some reason, wash your hand. Treat it like you touched the lead. Because if you accidentally eat it, it's far more dangerous than any of these other two. So that's alpha ray. It has the least penetrating power. The one with the next level of penetrating power is beta ray. And I guess beta energies come in a lot of different range. The kinetic energy of beta ray, I think it comes from, I've seen numbers as low as 100 keV and as high as, I don't know, let's just say 1 MeV. So in terms of the energy, the beta ray isn't all that different from alpha, but the beta rays are more penetrating. They would definitely go through paper, and but they get easily stopped by pieces of metal. Like aluminum is often used in beta ray shields. Sometimes people just have a thick plastic as a beta ray shield. So it goes through materials better, but not as well as the next thing in the list, the gamma rays. And the gamma rays are the ones in the energy range of, well, I say kinetic energy, but it's all energy. Kinetic energy of around 1 MeV or higher. So it goes through almost everything. And we like to think of lead as blocking gamma rays, but the thing is, if you need a pretty thick lead to block gamma rays well. So I forget, it depends on the energy range. If we are dealing with 1 MeV, to reduce the amount of gamma rays by a factor of 10, I think you need a thickness of about a centimeter of lead, which is not, which is not small. And if you have to reduce it by a factor of 1,000, then you need now inches, feet of lead instead of just a centimeter. So that's how these particles are characterized. And you can kind of maybe guess from these drawings, but I shouldn't play coy too much and just give you what these particles really are. Because back when they were studying this radioactivity, we are talking about early 1900s, late 1800s, they didn't know what these were. But today we know. Gamma ray, I think this is the one that you guys already know, so let me just spit it out. It's a high energy photon. So really, in characteristic, gamma ray is the same thing as X-ray. X-ray is a photon. Gamma ray is a photon. And at low energy limit of gamma ray, it will be indistinguishable from high energy limit of X-ray, because it's the same thing. And so when you think back to here, the component of radioactivity that was behaving like X-ray, that was the gamma ray. So that's it. So that's the component of radioactivity that penetrates through most material. Beta ray, depending on the source, may not have penetrated through desk material or whatever. Yeah?
What makes beta rays, just out of curiosity?
What makes beta rays?
Yeah, like would there be like a natural element you use, or can you produce it by using electricity and stuff?
So let me tell you what beta ray is.
Okay.
What beta rays are, they are electrons.
Because I know for work we use it. That's why for like non-destructive testing to test the body of an airplane.
Yeah.
I know you shoot beta rays at it. You have to stand behind like a shield.
Uh-huh.
And then you can see if there's cracks developing in the actual frame without taking the skin apart.
I see. So if you're calling it beta rays, whatever device you're using must be based on some kind of radioactive element.
Yes, that's why I was wondering
Yeah.
what was in it.
Yeah. Now you could do the exact same thing with the cathode ray tube. The only difference is that if you're using this, you would need a power source. Whereas if you're using a radioactive element as your power source, then you don't need a separate power source. So there are some common elements used. I think tritium is a common one. There are some emergency lighting that's based on beta ray. As in, they have some tube with a fluorescent coating, and the tube has hydrogen gas in there with some fraction of tritium, which is hydrogen with the 2 neutrons stuck to it. It's radioactive. It decays by beta decay, and so, yeah. Does that answer your question? Yeah. So here's one thing I want to point out now. We have 3 different names for electron. There's electron, there's cathode ray, there's beta ray. So when you use these 3 different names, it depends on the context. And I will tell you, I have at least 3 different names. I have the name I go with you guys, Andrew. I have my Korean name that my family sometimes calls me. And I have another name that I use with the people who can't pronounce my Korean name. It depends on the context. When you see electron just by itself, not doing anything, then you call it electron. When it's in a tube, in a device like this, that's designed to shoot out the electrons with high energy, you call it cathode ray. When it's coming out of a result of radioactivity, like from some decaying element, you call it beta ray. So those are all the same names for one and the same thing, electrons. Oh, I guess one thing I should be careful with is sometimes what we call beta ray may not be an electron. It could be something called positron. It's a version of an electron that has a positive charge. So I think that's also called beta ray. We don't have a separate name for that for some reason. And alpha ray is the most complex one. And I guess I should give you the simplest description of alpha ray. What it is it's a helium-4 nucleus. Do people know what I'm talking about when I say helium-4? I don't think we've talked about isotopes yet. Have we talked about isotopes? Okay, we need to talk about isotopes. So when we talk about isotopes, this will all make sense. We'll just leave this here. This is actually, if you take a helium, commonly occurring helium, take away 2 electrons, then you get what's at the core of alpha ray. It's just that, so we call it alpha ray when it's coming out of radioactivity decay as a result of radioactivity decay. Yeah, question?
So why is gamma a radiation and X-ray isn't radiation? Like why do we call gamma rays radiation?
Oh, they are both radiation. So I guess there are 2 similar sounding but different words. Radiation and radioactivity.
Oh, I see.
Radiation refers to anytime something is radiated, something transmits energy. In fact, this beta and alpha, they are not even electromagnetic waves. But these rays are emitting energy in some way, so we call it radiation. And the thing to be careful about is they are ionizing radiation. And your textbook actually goes into more detail of how these, how they were separated and how their properties were determined. And it's an interesting physics problem because this would be one way to do it. You have a radioactive source, which may be a source for all 3 different types. And you would distinguish them by, well, beta ray bends more, so it must be lighter. Alpha ray bends less, so it must be heavier. Gamma ray never bends, so it must be neutral, electrically neutral. And you start ruling out things, and at some point you look at the charge to mass ratio, and charge to mass ratio of beta ray happens to match charge to mass ratio of electron. So you guess there must be an electron. And charge to mass ratio of alpha ray somehow is, I guess, small enough to match that of a helium atom. Or helium atom if it lost 2 electrons. So that's how people guessed that alpha ray might be helium nucleus. And I don't know if your textbook covers it. There's a story of how Rutherford actually determined that it is actually helium atom. He kind of emitted the alpha rays into a vacuum chamber, and then vacuum chamber that was all vacuumed out, and then later on he actually detected the helium that must have been produced from the alpha rays by recombination. Oh, all right. How many here know what isotopes are? Some of you. You've heard the word, so let's just make sure to cover the ground on everything. So in chapter 8, we weren't really concerned with atomic nucleus. We are just dealing with the electrons around the atomic nucleus. The nucleus is whatever it is. Now we are not worried about the electrons at all. Instead, we are concerned with, well, what's at the core of the atomic nucleus. And this is, I don't know what it's supposed to be. Why did they have to draw so many? So, all right, let me count protons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Assuming there aren't any that's not visible, that must be oxygen and I can't. Neon. This must be neon nucleus, maybe. So you guys already know about protons, right? From hydrogen atom. Proton was the thing that's at the core of the hydrogen atom. So we can start listing properties of proton and neutron separately. So properties of proton would be that it has charge. The charge of proton is plus 1e, the elementary charge or the same magnitude of charge as electron, because that's how hydrogen atom is electrically neutral. And the mass of the proton from the mass of the hydrogen atom is approximately, mass of the proton is approximately 1000 GeV per c squared. That's the unit I have it memorized. 1000 GeV, that's not right. It's about 1 GeV or 1000 MeV. So let me just write it as 1 GeV per c squared. That's the mass of the proton. All right. So that's proton. You know it exists because that's at the core of the hydrogen atom. What do we need a neutron for? Like, why would people, well, let me tell you one of the properties of neutron. You can kind of guess it from the name itself, neutron. So one of the properties of neutron is that it has charge of 0. Like, why would you even, why are you introducing something that has 0 electrical charge? So it must be interacting with nothing. Like, why are you even bringing it up? Hint for that is in the periodic table. Do people know the history of how periodic table was initially constructed? How was it initially constructed?
By chemical property of elements.
Not by chemical property. I mean, chemical property plays a role, but someone had an idea to order the elements by one particular property. What was that one particular property? Well, they didn't know how to count the number of protons. They didn't even know about protons. Weight, atomic weight. Yeah. They had ways of determining atomic weight. So they listed it by, I think it's probably this one that'll work. So they did it by atomic weight. And once they started listing it by atomic weight, that's when they noticed the periodicity. So hydrogen kind of, well, it defines the baseline. So hydrogen has atomic weight close to 1. It's not exactly 1 because carbon-12 becomes the standard. You guys know that, right? Okay. Now, here's a funny thing. When you go to the next element, helium, your atomic weight doesn't go up to 2. It goes up to 4. So if you're counting number of protons, you went from 1 to 2 protons. Why isn't the atomic weight 2? Why is it 4? So that's where people start thinking, okay, there must be something that's not quite like a proton, but maybe weighs similar to proton. So let's just say mass of the neutron is also approximately 1 GeV over c squared. So what you're guessing is that with the helium, well, it must have 2 neutrons in it in addition to 2 protons. And let's keep going. Oh, wait, I don't want to scroll down that far. Okay, kind of jumps around. So when you look at, you can't really read it. With the lithium, 6.9, so about close to 7. So on average, lithium must have 3 protons and 4 neutrons. All right, my neutron numbers are increasing. Same thing with the beryllium, about 4 protons and 5 neutrons. And let's just keep going and see what happens. I want to just get up to carbon at least. So boron, 5 neutrons, 5 protons, 5 or 6 neutrons. Carbon, is carbon-13 also stable?
Yes.
Okay. So carbon-12 is where atomic mass unit is set. The definition of atomic mass unit is set so that carbon-12 is exactly 12 in atomic mass unit. But when you look at the average, there's enough carbon-13 out there in the world. That average comes up to 12.0. So carbon has 6 protons and 6 neutrons. Are you beginning to notice a pattern? Kind of equal number of protons and neutrons, right? But it's not an absolute law. It's kind of we are at an odd place. But so what we know or are guessing at now is that in the nucleus of the atom, you have two different types of particles. Because otherwise, there's no explaining the pattern of the atomic weights you see. There must be a particle that has charge, and there must be a particle that has no charge. And the kind of pattern you see makes most sense if you assume that these two methods are very similar. And this is where the idea of isotope comes from. So the number of protons determines what element you are dealing with. So for example, helium has two different isotopes. I don't know if this is all that helpful. Yeah, it's not all that helpful. I'm just going to write. So helium has, there are two stable isotopes of helium. So let me use that to introduce some of the notation that I'm going to start using. This is kind of where we start. Isotopes of element. So you guys have some sense of what iso in a word means, right? Or iso, or isos. Like what? Equal, isosceles. So when you start something with iso, it means something is equal. And what's equal? Oh, actually, I don't know what TOPS stands for. I don't think it stands for weight. Because I don't think, all right, I'm just going to leave it there. So it has an equal number of nucleons. It has, when you're referring to an isotope of a particular element, you are looking at the particles which have the same number of protons and neutrons. This is what I mean. So elements are things like hydrogen and helium. So hydrogen is an element, and helium is another element. And what makes them distinct elements is their distinct values of Z. So with the hydrogen, Z is equal to 1. And what this really is the number of protons. And with the helium, Z is equal to 2. And this determines all the chemistry that occurs with these elements. Hydrogen having 1 proton in the center, that gives a particular energy levels for the electron that's around it, and that makes certain kind of chemical reactions happen, certain kinds not. Same thing with the helium, with the 2 protons in the center. To make it electrically neutral, you need the 2 electrons around it. They fit into particular orbitals that produces certain kind of energy levels. That's what determines all the chemistry that you see. So these are the chemical elements. But it turns out there's more than one type of particle that has 1 proton in it. So those are isotopes. And the way I prefer to mark isotopes is this simple notation, because you can type it. They are, you list them this way. The name or symbol for the element, hydrogen, and you follow it with its isotope weight. So hydrogen 1 would be hydrogen, something you already know. And hydrogen has 1 more stable isotope that's not as common as hydrogen 1. It's a hydrogen 2, or it has its own name because it's simple enough to have its own name, deuterium. Anyone here have heard of heavy water? Like what makes heavy water heavy? Yeah, it has deuterium in place of hydrogen. So that's why it's heavier. It has more neutrons. And hydrogen has 1 more unstable but long-lived, like 13-year half-life of isotope. That's the tritium, or hydrogen 3. So these are the isotopes of a hydrogen. And the 2 stable isotopes of a helium would be these. So you have helium, I'll go in the same order. Helium 3 is much less common. It's very rare, but you have helium 3, and you have helium 4. That's the most common version of helium. That's why the atomic weight you saw was mostly 4. There's not much 3 in there. And I don't think helium-5 is stable. So that's what, when we talk about isotopes, that's what this refers to. So when you look at one element, helium, it has, so both the helium-3 and helium-4, chemically, they are near identical. Any kind of reaction helium-4 undergoes, which is not many. It's one of the noble gas elements. So helium-3 is also a noble gas. Any kind of reaction you can have with, that's how you have heavy water. Because hydrogen forms bonds with oxygen, 2 hydrogens to 1 oxygen forms water. You do the same reaction with the deuterium, you get heavy water. So these different isotopes, they don't affect any of the chemical reactions most of the time, but they will affect the nuclear reaction. So for example, this tritium, it can decay into helium-3 in a, well, I guess we were just talking about it, in a beta decay. But it wouldn't decay into helium-4 for reasons we'll go over in a little bit. Okay. So there's one kind of good fact for you to know. So you guys notice the pattern of the atomic weight, right? As you are going higher up in the number of protons, you are seeing that the kind of number of neutrons was increasing to catch up. But it's not really a hard and fast rule, because with hydrogen, this is stable, and that's the most common isotope of hydrogen. So obviously it doesn't need a neutron. And when you look at, well, I guess helium-4 actually does fit that pattern, 2 protons and 2 neutrons. But then you look at lithium, which has 3 protons and 4 neutrons, so what gives? So you don't have any clear pattern or like clear hard rule you can apply. So somebody just plotted all of them. This is a sort of a plot of stable atomic nuclei. So you can kind of see the pattern. So especially at the lower end, you see that the number of neutrons is often equal to the number of protons. If you have 10 elements with 10 protons, I guess that's neon, then you are kind of likely to have a stable isotope with 10 neutrons. So let's double check. What's the atomic weight of neon? So when you look at neon, yeah, atomic weight of neon is about 20. So 10 protons, 10 neutrons, approximately. Now, as you start to go into higher and higher Z value, or higher number of protons and neutrons, it starts to now skew in favor of neutrons. So when you get to very heavy, so uranium-238, I guess it's around the G value of 80, 90 or so, then for stability, you need, well, uranium is not stable. So you need more neutrons than protons to keep it stable for some reason. And you can kind of see there's an illustration here. Let's look at lead. Lead, G value of 82. It has 82 protons. Atomic weight, average of 207, or on average it has 125 neutrons. So that one-to-one pattern starts to break up, and that's what you see here. And I guess intuitively, this is how you would understand it. So, oh, yeah, this is the more, I probably should have led with this. This is a more beautiful diagram. So this is the figure that kind of gives you an intuitive sense. So one thing I have to tell you is that when you look at the atomic nucleus, something should tell you right away that this involves forces that you haven't seen yet. Because what fundamental forces have you seen so far? Electricity and magnetism. And you also seen gravity, but it's so weak compared to electricity and magnetism, it's not worth mentioning. So when you look at this, based on electricity alone, it shouldn't hold together. Because all these protons are positively charged, they should repel each other. And neutrons don't do anything. But somehow, they are being held together. So what people assumed was there must be another kind of unknown force, a nuclear force that's binding them together. And the easy assumption to make is that neutron is actually very similar to proton. Their masses are similar, their spin is exactly the same. The only difference is their charge. But charge is electromagnetic. Maybe it doesn't matter to nuclear force. So you would assume that there's a second unknown kind of force between these particles. Let's just say they are attractive. So whenever you have a neutron, that's contributing to that attractive force. And two protons would also attract each other too, except there's an electrostatic repulsion. So the balance of it is that two protons would repel each other. That's why there's no stable version of helium-2. With no neutron, there's not enough attractive nuclear force to hold it together. And with that kind of intuitive, rudimentary model, what you would guess is, well, the most place where this balance is held, as in the nucleus is not being crunched too much, or there's enough attractive force to keep it together, is usually the balance of where the number of neutron and number of protons are the same, except as you go into higher z value, the long-range repulsion of the electric force becomes more important, so you have to kind of keep piling on more neutrons to keep the whole thing stable. So that's sort of where we want to leave the nuclear forces with. We probably won't go into much more than that. Welcome back. We are changing the order around a little bit. I want you to start out with this. So we are back in section 10.4 of your textbook, nuclear reactions. So we'll do the detailed calculation later, but what I wanted to do was kind of set the stage so that we can note how special the thing that we are going to call fission is compared to other common, everyday nuclear reactions. So these nuclear reactions, radioactivity that results in these, I erased them all, alpha, beta, gamma particles, gamma rays, they usually happen in a decay process. So the process that produces alpha ray is called alpha decay. Process that produces beta ray is called beta decay. So I have a couple examples of the alpha source that I happen to know. Americium, I think 241 is right. Let me just double check. Americium 241. If I guessed it right, then it'll be talking about smoke detector somewhere. I don't know. Isotope, radioactive, most common. Where?
The last sentence in that one.
Smoke detector, yeah, okay, 241. So americium 241 undergoes alpha decay, and that's used in smoke detector. So the first question you could ask is, well, what does it decay into? Because we still hold to the conservation principles of, well, I don't know if I want to say conservation of mass, but there's something being conserved there. We don't want to just say, I had americium 241, it all goes to alpha particle and then it's all gone. That's not how it happens. So I guess this is how you can look at it. I think I can tell you this. There's a conservation law of nucleons. Nucleon, so nucleon, meaning this is the word used to refer to either proton or neutron. So if you want to talk about particle that's at the atomic nucleus, but you don't want to be specific about is it proton or neutron, you call it nucleon. It's the particle in the nucleus. So we can still hold to the idea of conservation of nucleon. So americium 241, what I do know is that number of proton plus number of neutron is 241. Right? Now, in the alpha decay, I think I need to tell you this. The number of protons or number of neutrons, they don't change. In an alpha decay, all that happens is these just get rearranged. So that means in an americium 241 alpha decay, Well, you know one thing. You know it emits an alpha particle, right? So it emits an alpha particle. I'm going to call it by its proper name. What it really is, it's a helium-4 nucleus. So this is going to carry away 2 protons and 2 neutrons away. Good? So whatever is remaining here, I kind of know its weight. 241 minus 4, so 237 of something. This is where I have to refer to the periodic table because I don't, but this is going to be my common excuse. I'm not a chemist, so I don't know where the elements are necessarily. I can kind of find them. Okay, here's the americium. Okay, I think it decays into neptunium. That's americium. Take away 2 protons, you get neptunium. So what americium decays into is neptunium-237. So this is an example of alpha decay. And you can do the same thing with the processes that produce beta rays. So the kind of one easy beta source that I know of is tritium. So you can do the same thing here. The tritium, oh, wait, let me finish here. So number of proton here is, oh, wait, I can just copy from there, right? 94. And number of neutrons here is 143, right? And so when you, so americium, yeah, 96 and 145, yeah. So with the beta decay, what the one interesting thing that's going to happen is that the total number of nucleons won't change, but the total number of protons or neutrons alone will change. So when you look at this, so this says 1 proton and 2 neutrons for a total of 3. And it decays in a way that it turns into helium-3. So it now has 2 protons and 1 neutron. So, okay, so the total number of nucleons is same. And it emitted 1 electron. So there's going to be one more quantity that we want to say is conserved. Anyone see that? Or let me put it another way. I kind of told you that tritium decays into helium-3. What if I didn't tell you? I only told you whatever beta decay process is, it emits an electron, and that's all you knew. How would you be able to guess what this daughter nucleus is, daughter isotope is? Like what principle could you maybe use?
Even what a beta particle is, an electron.
Okay.
You also need 2 electrons.
Not quite.
Like conservation of charge.
It's the charge that you're looking at. And I kind of see where Kevin was thinking of something that has 2 electrons because you start out with something neutral and you want to end with something neutral. So it's the same idea, except because we are dealing with the nucleus, we are kind of ignoring the electron cloud. So we don't want to think in terms of how many electrons does the atom have. We want to think about what change do we need to make to the nucleus so that the overall charge remains the same. So here, the overall charge, Q, is initially +1. So when you add up all the charges here, you want the total charge to also remain +1. So you have Q of -1 from this electron. So this must have charge of +2 so that they add up to 1. So that means it must have 2 protons, which means it can have only 1 neutron if we are conserving number of nucleons. So, so yeah, that's the beta decay example. So all these processes are, I guess, what I need to highlight is that these are all spontaneous processes. They have some half-life. It's determined by property of this and this isotope. And you can maybe calculate it, but it's not something you can really affect. It's a spontaneous emission process. These are all spontaneous processes. They have some half-life. It's determined by property of this and this isotope. And you can maybe calculate it, but it's not something you can really affect. It's a spontaneous emission process. Yeah? Now, what we are going to refer to as a fission is a kind of an activated emission or stimulated emission. So this is a very rough analogy, but you can kind of think of this as incandescent light, kind of emission that happens when something gets hot. And what we call stimulated emission is like the laser light. So that's what happens with the fission. So this is something that just happens in nature. You don't need any special arrangement of devices. It just happens in nature. Stimulated thing, you have to build a device that does that. So to make a fission happen, you have to have a device that you need to design a device to make that happen. So your textbook has a whole section on it. Let me just highlight some portions of it that I want you to be aware of before we look at a simulation. That's kind of fun thing to play with. So most naturally occurring isotopes, if you simply leave it out there, they're going to decay by alpha or beta decay. By the way, why am I not listing gamma decay here? Like, why no gamma rays? What makes one thing, what's one distinct characteristic of gamma ray that's different from alpha or beta ray? Massless, and also no charge. It's a photon. So gamma ray emission usually happens when an excited state of nucleus goes down to a lower or ground state of nucleus. So you are changing the state of nucleus, but you are not changing the composition of nucleus. That's why I'm not listing it there. There's no real gamma decay, and it's not one that we can kind of do it by identifying what kind of isotopes you are dealing with. So these are kind of simple reactions, right? You start out with one, it splits into multiple things. Fission reactions, you don't start out with one. You start out with several. You start out with two. So this is an example of fission reaction. We can just look at one of them, because kind of what happens on the right-hand side, there's many different possibilities. So what I really want you to pay attention to is the left-hand side, your starting element. So when you have an isotope sitting by itself, it wouldn't undergo fission on its own. Like if it's something that's going to do that, it would have been something so unstable that it wouldn't be there in the first place. So in a fission reaction, it's a stimulated process. You have something else that's impacting that nucleus, neutron, impacting that nucleus, that's causing a kind of unstable state to occur first, and then it splits off. Here's a kind of schematic diagram of like how it happens. This is the schematic picture of it. I mean, it's a simplified picture, so I don't want you to take it too seriously. But you have a fissile atomic nucleus, and not everything undergoes fission, because sometimes you can have like uranium-238. If it's struck by a neutron, it'll become uranium-239, and it'll quickly undergo beta decay into plutonium-239. It doesn't undergo fission like uranium-235 does. Uranium-235 does. So when a neutron hits it, it becomes this unstable state of uranium-236. And this is not a long-lived state. It quickly splits into, so this is the fission reaction. This is the fission, or I think fission means like splitting things, right? So it's, this process splits the nucleus into two parts, not always evenly sized, sometimes one's bigger than the other. In this fission process, it releases some amount of energy. And here's an actually important part. It usually releases some neutrons. And usually, so this is the property of the material that we call fissile, meaning fissionable. So a fissile material would undergo such a reaction that on average, it releases more neutron than it took to cause that fission reaction to happen. So uranium-235 is one of those fissile material, which is why. How many, North Korea has been in the news. What's one of the first steps you go through? The step that Iran was going through, that when you're first trying to develop the atomic bomb. You have to enrich uranium, right? What does enriching uranium mean? Isolate uranium-235. So in the naturally occurring quantities, it's mostly uranium-238 and maybe like 0.1% uranium-235. And they are isotopes, meaning they undergo the same chemical reaction. So they are difficult to separate out. And people developed different processes. You can look it up later. Just do carefully. So the goal of someone trying to design atomic bomb or make atomic bomb is you have to separate out enough of uranium-235 so that you have a pure sample of uranium-235, not as much of uranium-238. And when the fuel that you're putting in reactors, that's only a few percent uranium-235. Medical research reactors sometimes go as high as 20, 30, 40% uranium-235. Weapons grade, I think it needs to be 90% and up, 95, 99%. So that's kind of what you monitor to see, is this country building atomic bomb? So Iran is, I think, at like 40%, so they are not at the level to build an atomic bomb. But when they build facilities that can enrich uranium up to 95, 99%, that's when you see, oh, you're trying to build a bomb there. There's no other reason to have that. So this is the key components of a fission process, that you need to have an initial neutron that's going to start the sequence of events. And the thing is, this one reaction, it doesn't release that much energy. So what you need is a chain reaction. You need to start out with one neutron, and you need this to kind of start more reactions like it. And that's where this reaction producing more neutrons than it used, it becomes an important part. So there's a simulation to kind of demonstrate this and why it's, so to get the chain reaction of kind of this type, why it's important to have a pure sample of uranium-235. And it's a PHYS simulation. Let me just demonstrate, at a conceptual level. So it's it's kind of schematic version of fission reaction, and you can do it with one single uranium-235. You shoot a neutron at it. Undergoes fission. There it is. So that's the single reaction. That's kind of, all right, so the schematic explanation of what's going on when you see fission. But other than that, and it's producing 3 neutrons, and it's the version they are showing. So it's the chain reaction one that's kind of interesting. So what you have in nature is kind of like this. It's where you have, let's actually have it even more than nature. Let me have it be 50% uranium-238 and 50% uranium-235. Actually, maybe, let me see if I can show you the uranium-238. So if I have, I need to have a target. Okay, there's, I think, at least one in the path, right? So this is what uranium-238 does. So it becomes uranium-239, and uranium-239 doesn't undergo fission. It is still unstable. It has a relatively short half-life, and it'll decay into plutonium-239, which is, once again, fissile. But because of the time scales involved in there, this doesn't undergo fission. So what uranium-238 represents in any reaction is, watch what happens. I start out with 1 neutron. How many neutrons do I have? 0. So wherever you have uranium-238, it absorbs neutron. Like it uses up your neutron and it doesn't give any neutrons back. So that's what you will see happening when you, when I have some uranium-230, about 50-50, some uranium-235 and uranium-238 kind of embedded in it. So the reaction will kind of start, and the uranium-238 kind of acts as a shield for these uranium-235, because these absorb the neutrons. So there were these uranium-235 that never got to be hit by a neutron and no complete chain reaction. And this is why when you are building a bomb, there you need to have a pure sample of uranium-235. And the second idea that I can demonstrate with this simulation is the idea of critical mass. So like when you have one uranium-235, that's kind of simple. What would happen? It splits and that's it. Now, what do you think would happen if I have, I don't know, 10 uranium 235 nucleus and I fire one neutron into it? Well, let's try it and see. Let's try it and see. All right, some of them went off, but not all of them, right? You can kind of see why, right? Yeah, I mean, I don't have, so each time my neutron hits on uranium-235, the neutrons kind of go in random directions. So there's some chance of hitting another uranium-235. But if they are too far spread out, then it can escape, not do anything. So when you have a critical mass of uranium-235, this is what happens instead. Let me put a, I don't know how many is critical in this simulation. Let's try 50. When you have 50 uranium-235, and I fire one into it, then this is the kind of kaboom that happens in atomic bomb. So almost all of it reacts. Because, so once again, when you have dense enough collection of uranium-235, then the first neutron hits it, the neutrons are going in some random direction, and it has a decent chance of hitting some other uranium-235 before it escapes entirely. And because with each reaction, you are getting even more neutrons, the more of these there are. Like once it's all flooded with the neutrons, almost, well, no, okay, not everyone. Good fraction of them, like 44 of them, will be hit by this neutron somewhere in this cycle. So that's the basic principle in building atomic bomb. This is not anything that's a secret, that's public information. The basic design of an atomic bomb is you have two subcritical masses of uranium-235. The pieces that are too small to result in chain reaction. And you bring those two subcritical pieces into each other as quickly as possible, so that as some, like in a blink of an eye or less than that, in a nanosecond or so, you have a critical mass, and then this now blows into pieces because then it's this setup. So there's, I guess, some bomb designs have a neutron source in it, but even if you didn't have a neutron source, some component of radioactivity will involve some stray neutron, so it'll kind of result in something like this once those subcritical pieces are brought together. So that's the idea, but even though now, let me just add some isotopes of uranium-238, kind of what you would have in nature, close to, right, something like that. About 30% uranium-235, 60-some% uranium-238. Watch what happens, how the presence of uranium-238 kind of changes things, right? So the chain reaction that was able to happen before, like, so, you know, once again, the chain reaction. All right. So I haven't taken away any uranium-235, but by simply adding these, you prevent that chain reaction from happening. It's because those three neutrons that are going out, it gets absorbed by this non-fissile material. So that's the basic idea in fission reaction. It's Now, there's more complicated calculations there, like mean free path and how much material, what's the actual critical mass. So that was a big part of the Manhattan Project, where that's the part that scientists would work on. The scientists like Feynman, they would work on that calculation part of, well, how big a piece of uranium-235 do you need for it to be a critical mass and it's going to go kaboom. And you can't try too many of those because it's not something you just simply build in a lab. The moment you build it, it goes kaboom and you die. And in fact, that if you read some of Feynman's writing, you will read him relating to how he saw the technical workers. During World War II, they had a strategic division of labor. So the workers working at the enrichment facility, they didn't know what it was they were working with. So they were storing fissile materials together in a way that they could become critical mass the way they are stored. So, and I guess it's a kind of, when you read it, it's a sort of a cautionary tale on why even people who are not theoretical physicists know the basic theories of the material you're working with so that you know when things get dangerous. So in fact, I guess with radioactivity and nuclear physics, it's a kind of, it's a history is riddled with when people didn't know how dangerous the material was that they were working with. Marie Curie, people think she died of chronic radiation, or I don't know what the correct term is. It's a long-term radiation poisoning because the early workers didn't realize just how dangerous radioactivity was, so they were overexposing themselves when they really should have taken precautions.
When we are talking about nuclear fusion, we are, in some sense, talking of an opposite process from fission. So, so as we are considering nuclear fusion, I do think it is good to contrast it with the nuclear fission that you have seen. In the case of fission, the kind of reaction that you have seen is, well, fission or a separation of a heavy atomic nucleus. So the example that you see in the textbook and in the lecture is a fission of uranium-235 isotope. The kind of the structure of the atomic nucleus that allows a fission occur, it's quite specific to a particular isotope. So take uranium, for example. Uranium-235 is fissile, it undergoes a fission. And uranium-238, it's not fissile. And at least at our level of covering this, I'm not going to give you an explanation why one is a fissile and one is not. But this is the process that occurs in fission. And one of the things that tells you that fission is a kind of a process that can happen is when you look at the atomic masses. So you look at the combined mass of the neutron and uranium-235. That'll give you the rest energy that you're starting with. And you look at the potential decay product of the daughter nuclei, then you will see that the final rest energy here, it's less than the rest energy that you're starting out with. So from that rough high level 30,000 feet view, you can see that when you have a neutron plus this heavy atomic nucleus, that it's more energetically favorable for this to split into smaller, lighter nuclei. So, and the details of the process that occurs, that's the part that I'm saying. It kind of depends on the particular isotope. We are not going to go too much into that detail. But at this, again, 30,000 feet view, you can see that it, just looking at rough numbers, that the process that occurs from the left-hand side to the right-hand side is energetically favorable. And in our previous discussion about fission, we ended at talking about how this is a kind of a stimulated process, that this is activated by collision of neutron with a fissile material. And in fact, controlling fission reaction has a lot with controlling the neutron economy. So I guess the best way to phrase that in a way that's not misleading is controlled through neutrons. I'll just say neutrons. And in fact, you see that aspect of that when you read about nuclear reactors. So in nuclear reactors, you have something called moderators. And I think moderators are something that you don't have in a nuclear bomb. But in a peaceful nuclear reactor, you have something called a moderator, and the role of moderators are really to control the neutrons. The neutrons so in the fission reaction produces their own neutrons, and these neutrons that come out of these reactions are generally high energy neutrons, and high energy neutrons are less likely to react with another fissile material to produce a fission reaction. So the role of moderator is to actually slow down these neutrons, make the reaction more likely to happen. And I think way back in, is it 2013, with the last well-publicized nuclear disaster in Fukushima, one of the things that you might have heard about was the water in the nuclear reactor. The water in the nuclear reactors in some designs, serve a dual role as the neutron moderators, which facilitate these nuclear fission reactions to occur, and also as a coolant. And at some point when the pumps weren't working because the electricity was out and water wasn't circulating and all of that. So that's a fission. Those are the details that we consider when we are thinking about fission. And when we are thinking of nuclear fusion, the kind of the details that we are concerned with, it actually changes quite a bit. The things that we worry about when we were thinking about fission, a lot of that kind of doesn't matter anymore, and new considerations come into place. Because in trying to get fission reaction to happen, a lot of that actually really deals with the neutrons. That's the key number one thing that you think through. Whether a material is fissile or not, it really has to do hey, how many neutrons does it produce in this reaction that it splits it apart? If it produces too few neutrons, then it's not fissile. If it produces enough neutrons, then it is fissile. With a nuclear fusion reaction, that doesn't quite, it's not the primary concern. And so the nuclear fusion reaction is kind of what it sounds like at the fundamental level. It involves nuclei, or the atomic nucleus, fusing, coming together and becoming a heavier isotope. And as you think this through, I think you will see that there has to be more steps involved here, because imagine the simplest possible fusion process. So the simplest possible fusion process would be a hydrogen fusing with another hydrogen, and then turning into what? Helium-2. That hopefully, if you are paying attention through this chapter 10, that's not quite right, because helium-2 is not one of the isotopes of helium that you are familiar with. You have heard of helium-3 and you have heard of helium-4, but helium-2 is not. It's not one of the stable isotopes of helium. And in fact, one of the things that you have seen leading up to here is the island of nuclear stability. So just to briefly sketch the chart, what it looked like was, if you plot for every stable or long enough lived isotopes. If you plot the number of neutrons and number of protons, the kind of the stable isotopes, they more or less follow a straight line until you get to the more heavier nuclei where there are more neutrons than protons. So if you are thinking of forming these heavier isotopes here from these lighter isotopes here, then starting with the hydrogen, which only has proton, at some point you have to turn some of these protons into neutrons. And so this is the more detailed portion of the process that I wouldn't trust myself to remember, mainly because I'm not an astrophysicist and I don't think about these particular processes too often. But your textbook does mention this in the portion where it talks about the nuclear fusion reactions that take place in the sun. That's the what they call the proton-proton chain. And this is describing how, starting with hydrogen, the most common, most abundant building block in the building block of normal matter in the universe, you would get to the next heavier isotope, to helium. So it's describing this chain, proton, proton. It forms this, and I guess, yeah, helium-2 never really forms. So in this process, one of the protons become a neutron, forming a deuterium. And as the one of the proton becomes a neutron, charge is conserved, so it produces an not electron, produces a positron, and it produces this one more particle that we are actually a week early to talk about, neutrino, which I kind of hinted at the very last lecture in this chapter, but we will save the introduction of neutrino until next week. But it does that. And this positron, it'll annihilate with electron within the sun and go away, turn into gamma rays. All of that is for next week. We haven't started talking about antiparticles yet. But so hydrogen plus hydrogen becomes deuterium plus some other things. And hydrogen plus deuterium now becomes helium-3. And helium-3 is not the most common isotope of helium when you look into the sun. So this helium-3 and helium-3 combines and becomes a helium-4 plus some spare protons, and these will go through this proton-proton chain to make more helium-4. And all this process is basically adding up to how this is describing how hydrogen is fused into helium in the sun or any star that we imagine. Sun is the nearest star that we know, and it's the most closely studied star. And we think, based on astronomical observation, this is the primary process that occurs in all the stars, all the new stars. And as you are thinking about this process, there are really the two biggest thing to consider, which are the barriers that need to be overcome. So one is, so far we've been drawing diagrams, but I want you to really remember that when we describe hydrogen, or technically proton, in these interactions, we are talking about two positive charges that somehow have to come near each other to the point where nuclear forces become appreciable. And as we will talk in detail next week, nuclear force is a short-range force. The strong nuclear force, it has somewhere around the range of 10 to minus 15 meter. That's about the size of the atomic nucleus. Outside of that, it starts to become negligible. So these two protons have to come 10 to the minus 15 meter of each other before the nuclear forces can take over the electromagnetic force that governs most of the other interactions that we are familiar with. And what I want you to consider and realize is that these are both the positive charges. It's just the way things are arranged that both of the particles that would participate in this nuclear reaction, they both happen to have positive charges. And until they come close enough to the range where nuclear force can take over, these two positive charges are actually experiencing Coulomb repulsion. So if you had two protons simply near each other, the most common tendency is for them to simply repel each other and be as far away from each other as they can, and no nuclear fission reaction occurs. So there has to be something in the setup that overcomes this Coulomb repulsion, and that leads to the first of the considerations that is necessary for nuclear fission to occur. And what it is so just leading from here, for nuclear fission to occur, the fusion fuel, which in this case is hydrogen, but it can be other material too, the fusion fuel needs to have high kinetic energy. Because you can almost think of this classically. You can think of this as two positive charges that are moving towards each other. You need to get them to close enough distance where nuclear reaction can take over and allow fusion to occur. And so as they come close to each other, they're going to slow down. And for them to come close enough before they are turned around and repelled back, for them to come close enough, they have to start out with a high enough kinetic energy so that before the classical turning point, they are close enough so that fusion can occur. And in the more high kinetic energy, if you are looking at those each individual microscopic interactions, or from the macroscopic perspective, you would say they need to have high temperature. So that's one of the conditions that needed to be. And as you continue to look at this reaction carefully, what I think you will see is that this reaction describes a fairly unlikely set of circumstances. So for the proton chain that's occurring in the sun, definitely. And we can actually cheat, or we can help it along by for example, providing deuterium. So if you are trying to set up the artificial conditions to make the fusion more likely to occur, nothing says that you have to start out with the hydrogen. You can get heavy water. You can separate deuterium, or I guess heavy water already contains the deuterium. So you can actually start out with the deuterium, or actually hydrogen has a even heavier isotope, tritium, that's actually fairly stable. So you can even get tritium and start out with some tritium to help this reaction along. So that is possible. And even in that case, what you're looking at is a fairly unlikely or rare set of circumstances, because this always involves repulsion. So if they happen to be coming toward each other with the wrong velocities, as in they're slightly missing each other, then it's quite easy for them to not come as close as they can, kind of miss each other. So there's quite of a set of circumstances that needed to happen right. You could say that the processes that are described here, they are on the whole fairly rare processes, especially after the first step, because this can't be just a hydrogen colliding with any other hydrogen lying around. It has to be colliding one of the deuterium. And here you have to find one of the helium-3 that's already formed, make the collide with another helium-3 that's also formed. And so all these are beginning to describe processes that are rare, or at least on the rarer side. And if you need, so this is a phrase that you will see me say sometime next week, which is, it's a saying in particle physics. It's saying whatever is not forbidden is mandatory. And it's a reference to the fact that all the rare things that could happen in particle physics, you actually do see them happen all the time. And the way we make those rare processes happen, we kind of guarantee that they happen, is we have a large number of them. We have a large number of incidences, large number of collisions, large quantity of data. Then within that large set, even the rare processes are guaranteed to happen sometimes. And really what you need is that these things happen often enough. And in terms of kind of material conditions, what you need is for the, let me call it less common collision processes to occur, the fusion field needs to be at high density. So these two factors are what's needed for fusion processes to occur: high temperature and high density. And this is the kind of condition that actually met in the core of a star like our sun. And in fact, that's the success of our solar model that describes the nuclear fusion that powers our sun. It keeps the sun in hydrostatic equilibrium. The energy that the sun produces, it's no longer coming from gravitational collapse. It's coming from the energy released in this fusion process. And I think with some sense of scale for how large the sun is, how much mass there is, I think it's easy enough to imagine that in the core that it would be at high enough density, that the hydrogen atoms that are in the core are so packed together that it's a much higher density than anything else we have on the Earth now. And I think even high temperature part is kind of easy to imagine, sometimes kind of through the wrong process, but I think what's important is that this is something that happens. Now, it's one thing to understand the nuclear processes in the sun, which is, it's an accomplishment of its own. And this is something that really helped us understand astrophysics and actually through the solution of what used to be called the solar neutrino problem, it helped to add to our understanding of the particle physics as well, because it helped us understand the neutrino, the particle we are introducing next week. So there's that. That's one thing. It's something that happens in nature, and we have a theory that describes. That's great. And maybe in another comparison to nuclear fission, what we are describing the nuclear fission, at least most of the time, this is not something that just happens in nature, or it doesn't really happen in nature, at least not anymore. I think there are some locations on Earth that used to be natural nuclear reactor, not around anymore. This process like this is not something that happens in nature these days. This is a device that we built. And so far in our description of fusion, we are simply describing something that just happens. We don't, this is not a process that we are driving. So one of the kind of goal or technology that's been always 20 years away has been generation of energy through nuclear fusion. And in one sense, that's right. I think your textbook mentions it somewhere. It should talk about fusion reactor. So fusion chain believed to be most practical for using a nuclear fusion reactor. And here, we are kind of cheating, start out with the deuterium instead of hydrogen, so that we have a shorter chain. And people have been doing research on devices like this. I think ITER is the name of the collaboration that does work on this. This is a kind of a confinement thing. And the goal of a device like this is really to produce these conditions in a controllable manner. They need to put together these light isotopes, where fusion is more energetically favorable to occur, we need to put them at high temperature, at high enough density, so that fusion occurs. And the challenge here is that no physical material can be used to actually confine the material, because these temperatures are so high that any potential container would just melt. So they use electromagnetic trap. I think they talk about something about very difficult problem, high temperatures are needed. Example. Yeah. Yeah, so they're not going into detail. The kind of confinement that they, so they use magnetic fields because fields can withstand any temperature. And the short story here is that a lot of work is still being done. There's work being done at National Ignition Facility. I think that's at Lawrence Livermore Laboratory, that they do fusion research there. And they can cause a fusion to occur. The problem is that it takes more energy to cause the fusion reaction to occur. Compared to the amount of energy they get out of the fusion reaction, they put in more energy. So it's not actually on net producing any energy. Now, there's one way in which we have been able to harness this fusion reaction in a practical way. And this is kind of the story of technology, which is the first place where they get used is for it's for war, because in fact a lot of the fission research was driven by the need during the World War II. And a lot of the funding for the nuclear fusion research has come through the time of Cold War, when United States was competing with the Soviet Union on who's going to build the biggest bomb. And that's what this section is describing. That so the fission bomb, the atomic bomb, has a limit to how much of an yield you can get, because as you heard me describe in the lecture on the nuclear fission, it's about bringing two subcritical masses together quickly to make a critical mass, and then the critical mass then blows up. So there's a kind of actual physical limit to how big of a pieces that you can bring together and then have a bomb go off. So if you are only relying on nuclear fission, there's a maximum amount of explosive power that you will reach. And at some point, the scientists who are working on the atomic bomb realized that using the explosive release of energy of the fission bomb, they can actually achieve these conditions and in a very short time scale. And by achieving these conditions in a very short time scale in a fusion fuel, they can actually ignite fusion reaction. And that's what's called a hydrogen bomb. So it's called a hydrogen bomb because the hydrogen bombs contain fission bomb in it, and the fission reaction is used to trigger the fusion component of it. And once you trigger the fusion component, then it's a kind of it's a self-sustaining reaction, at least until it burns through the deuterium and tritium fuel that's within the bomb. So for those of you more interested in reading about it, I will just say point you to one scientist. So Robert Oppenheimer was the project lead of the Manhattan Project that produced the fission bomb. And with a lot of physicists who worked on the atomic bomb, he really regretted working on that weapon of mass destruction. And Oppenheimer, Einstein, maybe Feynman, they all later on really regretted working on the A-bomb. And I don't think he really worked on the hydrogen bomb for that reason. A lot of these physicists, them working on that weapon of mass destruction, it's, during the World War II, they were fighting the literal Nazis. And it's kind of lesser of two evils still. there's one physicist who was central in the development of the hydrogen bomb, who wasn't Robert Oppenheimer, is Edward Teller. Yeah, Edward Teller is, I think he is the father of the hydrogen bomb. Yeah, so yeah, I think Teller was actually enthusiastic about working on the bomb, and Wheeler had his contributions, which is what I'm remembering. And yeah, it's thing. Yeah, hydrogen bomb. And yeah, and okay, I think I was somehow mixing up Edward Teller with John Wheeler, and I think so. I think the story here is it's good to read through, particularly what Wikipedia is calling Oppenheimer controversy. And I would just say, physicists are human beings. They have their shortcomings, and there are a lot of physicists who are working for Nazis, not in US, but you know, a lot of German physicists were working for the Nazis, and it's just good to keep in mind that scientists are not perfect. But hydrogen bomb, that's the only practical use of the fusion reaction that mankind or humankind has been able to control, and that's, I think, where we'll leave things off at.
So when we get to particle physics starting on Thursday, I want to use this as an example that led to a discovery of a new particle that we haven't talked about. Your textbook kind of mentions it out of sequence. So, you know, you can read your textbook if you want, but I'll pretend that I haven't seen that portion of the textbook. This is what you see in a tritium's beta decay. You see tritium somehow becoming helium-3, in the process emitting an electron, beta ray. So here's a question you can ask and answer. What would be the energy of this beta ray? And this is something you can calculate from the information you can look up. And the information you can look up are the masses of the tritium and helium-3. So let me start out with that. Energy calculation in beta decay. So I actually don't have those numbers, so let me look them up now. So mass of H3 is 2809.432 MeV per C squared. And I need to know mass of the helium-3. So mass of helium-3 is, okay, I'm going to write it down and I will explain one thing. 2809.414 MeV per C squared. You see the small difference here, right? Small, very tiny difference in mass. And that's where the energy released in the decay is coming from. But if you think about it too much, as in you think about the mass of the electron, which is 0.511 MeV per C squared, then this difference is not enough, right? And I've experienced this before, and this is why. When you look up tritium-3 mass, this is what they're giving you. They are giving you the mass of this object, something that has 1 proton, 2 neutrons in the center. And when you call something tritium, you are not just referring to the nucleus. You are also including the electron around it. So when you call something helium-3, you are not just referring to the nucleus of 2 protons and 1 neutron. You are also referring to the 2 electrons around it. So this mass that's given here, that kind of already includes the mass of the electron. So let me just change these numbers a little bit so that I can do the calculation the way I want to. So I'm going to say, so the nucleus of the tritium must be 2808 921. Then when you add this, you get back the original number, right? That's kind of the number I need to do calculation the way I want it as a nuclear reaction. So for method of the helium-3, I need to subtract off 2 of these. So it's 1.022. So it will be 2808.392. So, okay, now we have all the proper numbers. So this is what you see. When you have the masses on the left-hand side, that's this mass, and you add up the masses on the right-hand side, they don't add up to the same value. So the nuclear reaction is the first example where the energy difference involved is big enough that those energy differences actually show up in the masses you would measure. So here's the now interesting question you can ask. What is the energy of electron emitted in the beta decay of tritium? How would you set up that calculation? How would you do it?
Find the difference in two masses.
We have to be careful. So in the decay, does all the kinetic and all the extra energy, does all of it go into the electron? Let me just check your intuition. So Dimitri, I show you shaking your head. Why do you think not all of the energy goes into the electron?
Conservation.
Conservation of momentum, right? So if you have tritium, that's going to decay into helium-3 and an electron that's being emitted. Then if an electron is being emitted to one side, then helium-3 should be moving to the other side to make the total momentum 0. So let's do the calculation. I think I have just enough time to actually finish this calculation if I just go through it and not talk so much. So you do this calculation by starting with conservation of energy and momentum. Right? Yes. Did I tell you that all the relativity stuff, it's going to come back? Yeah. Yeah. So here, actually, you know what, let's do it as a non-relativistic calculation because I can kind of see from the amount of energy that's involved, it's going to be a non-relativistic thing. So let's make it easy for ourselves. So non-relativistic calculation. We have energy conservation, and we have momentum conservation. So from conservation of energy, so I'm just going to write down something that kind of makes sense to me. So I'm going to have rest energy of tritium is equal to rest energy of helium-3 plus rest energy of electron plus the kinetic energies of the helium-3 and kinetic energy of the electron. So that would be plus 1/2 mass of helium-3 times velocity of helium-3 squared plus 1/2 mass of the electron times velocity of electron squared. Okay, conservation of momentum. So my initial momentum is 0, and my final momentum, let's say electron is going to the right, so it's a plus mass of the electron, velocity of the electron squared, minus the momentum of helium-3, mass of helium-3 times velocity of helium-3, squared, not squared, yeah. All right, so I have these two equations. And the rest energies, I can kind of combine them. It will be, so really the only thing I'm concerned with, let me try to save a little bit of time. When I combine these all into one term, then what I get is just the difference in the masses, which would be this minus this minus this. Also, the difference is not that big. It's 0.018 MeV. For the rest energy, you really have to multiply it by c squared. So that's the difference in the rest energies. So this difference is equal to the kinetic energies. So 1/2 mhe3 vhe3 squared plus 1/2 MeVe squared. All right. I guess we were interested in the electron energy. So the thing to do is to solve this for the helium velocity, plug it in, eliminate it, and put them in a form so that it's expressed as electron kinetic energy. So I'm going to solve this. Sorry, I got only 4 minutes left. I have this that I'm going to solve for the helium velocity because I'm trying to eliminate that. So my helium velocity is this divided by that, me over mhe3 ve. Plug this in here. Then I end up with, I have this still on the left side, 0.018 MeV is equal to, plugging this in and then squaring, I get 1/2 Me squared times mhe3 divided by mhe3 times ve squared plus 1/2 MeV squared. Good. I can do a little bit of algebraic simplification. Let me do this a bit of an odd substitution. That's actually going to help me. I'm going to do this odd substitution. Kinetic energy of E as 1/2 MeVe squared. Then this is also kinetic energy of E. And I can actually find 1/2 MeVe squared here, which means I get a vector of kinetic energy of E here. So, which means I can factor out kinetic energy of electron. So here, all the remaining terms are a factor of Me. And actually, this cancels out a factor here. So divided by a factor of mass of helium-3. I think that's everything there, right? Plus 1. So solving for kinetic energy of the electron is just this, the total available energy divided by this. So total, it's going to be something close to the total available energy because this fraction will be a smaller than 1. So let's just to get a sense, to get the numerical sense. So electron mass divided by helium-3 mass. So the ratio is 2, well, so this is the number, or approximately 2 times 10 to minus 4. Or if you had used just 1, as in if you had assumed that this was the correct energy, kinetic energy, then you would have been off by by that factor, by 1.0002 or some number of zeros. So if you actually calculate it, it's a 0.018. So so this actually doesn't have enough of precision for that factor to matter. But let's just pretend that it was and do that, 1 plus that. Then whether you account for recoil energy or not, it would be a matter of, well, are you expecting energy of, so it's a matter of, are you looking at this versus 0.01799, okay, I need to write this down so that they are different. Now, here's the amazing thing. There are experiments where this difference counts. The accounting for the recoil energy of the resulting helium-3 actually matters. So this is the calculation we have. And from this, you would be led to believe that the energy of the electron coming out from this beta decay of tritium should be 0.018 or 18 kilo electron volts. What we'll go over either on Thursday or next week early is that that's actually not the case. When they actually do the experiment, they see a range of electron energies. And that's going to be a reason for discovery of a new particle that you have never heard about unless you're reading the textbook.